It's a pleasure for me to introduce third speaker this morning, close collaborator of Carles, Jiří Rosický from Brno, and he's going to talk about combinatorial and accessible model categories.
Yes, thank you. I am honored by the invitation to give a talk at the occasion of celebrating Carles' 60s. I think that we met Carles for the first time at Category Theory Conference in Tours in '94, quite a long time ago. And then I made good decision to come to Algebraic Topology Conference in Barcelona in 2002, which you organized. And since then we started to collaborate. And I want to say that this collaboration was always incredibly pleasant and fruitful. So I decided to talk today about something which Carles might like, so about combinatorial and accessible model categories. So let me to start just from beginnings. That a weak factorization system, I think anybody knows what it means, is cofinitely generated if there is a set such that there is the closure of this set under push-outs, transfinite compositions, and retracts. And the model category is cofinitely generated if it's both weak factorization systems are cofinitely generated. So it's a kind of smallness condition, very frequently appearing, and it's not somewhat immediately clear how to observe that some weak factorization system is not cofinitely generated. And in 2000, 20 years ago, Mark Hovey asked for examples of model categories which are not cofinitely generated, which is the same as asking for examples of weak factorization systems which are not, because any weak factorization system produces a model category if you take the other one consisting of all morphisms. So then that's and then weak equivalences are just all morphisms or isomorphisms. So which is not interesting, but it's an example. And one of the first examples of such which are not is due to my joint paper with Adamek, Herlich, and Tolen, that just to take both sets, partially ordered sets, and for L you take embeddings. And it's well known that both sets which are injective to embeddings are precisely complete lattices. And now, you see, I told you that it's not easy to recognize that this L doesn't satisfy the smallness condition with some observable results about that. And one of those observable results is that injectives, if it is covalently generated, then injectives form an accessible, you are on a local accessible category, then injectives form an accessible category, and complete lattices are not. So this is one of many examples of weak systems which are not covalently generated. So now, but there's something which is more general than covalently generated and still very interesting, and these are accessible weak factorization systems. So what does it mean? So I have weak factorization system. It means two classes of morphisms, L and R, which are, as I haven't mentioned, which are related by these lifting properties. So then any morphism factorizes into an L morphism followed by R morphism. And when this factorization is functorial, I will tell you immediately what does it mean. Then this weak factorization system is called accessible if this factorization functor. So what does it mean to be functorial? It means that you have functor going from morphisms to composable pair of morphisms, giving factorizations of morphisms, and it's done functorially. And it's accessible if this functor is accessible, which means that it preserves lambda to the Colbitz for some lambda. So this, and from the small object argument, it immediately follows then any cofinally generated weak factorization system in a locally presentable category is accessible. So these accessible are more general than cofinally generated. And I will give an example very soon of something which is accessible but not cofinally generated. And but there are some more structures coming out of this functorial factorization. So this factorization functors determines two endofunctors on the category morphisms. So the first one, just you take a morphism, you go to composable pair and you take the first member of this composition. So this is the endofunctor L, sending to each morphism this co-fibered part of its factorization. And the R says the fibered part, or trivially fibered part. So to any morphism, you take the second member of this composable pair. And this is formally explained here that you have these two projections sending a composable pair to this first or second morphism. So you have these two functors. So any factorization functor determines a pair of endofunctors L and R on your category K squared, which is the category of morphisms. And then the factorization is just that F is L of F followed by R of F. So this is just notation concerning these factorial factorizations. And now these functors have more properties because this functor L is copointed. Copointed means that you have a natural transformation from L to identity, which is given by since we are in the category of morphism, so this natural transformation should be a pair of things. So the first identity and the second is R or F. Just simply imagine your morphism F, and you have this L of F, and this R of F, the second member just is the copointing, transforming it to F on the domain its identity, and the codomain its R or F. And dually, R is pointed by natural transformation rho from identity to R, which again, the first component is L of F, and the second is identity. So certainly, it reminds you so-called algebraic weak factorization systems, but I will not go so far because I will just have just functors and L and R. I will not make them a monad. So and my L coalgebras are coalgebras for a functor. So what's an L coalgebra? So it's an object in the kind of morphism, and then it is a morphism in the category of morphism. So it's a pair of morphism from F to L of F, such that this morphism is split by the copoint. So this is the real definition of a coalgebra for a functor. Here you have a functor which is copointed, so coalgebra is a morphism which is split by the copoint. And it's easy to see that you can reduce it, in fact, to a pair F, which is this morphism, carrying this coalgebra. And since this U is identity here, it follows from this splitting. So you just have this V. And this V is in fact a morphism which splits R of F. So one can realize that this definition of a coalgebra for a functor L is the same thing that you take just a morphism and you take the splitting of this second component of this composition of R of F. So this is something very, very, very natural. So what are morphisms of coalgebras? So you have two coalgebras written in this way, that just is a morphism plus splitting of the second component. So morphisms are, say, morphisms on the category of morphisms. So these are pairs of morphisms. Here you have a diagram, then you can see it. So this is the first morphism F. So here you see its factorization. This coalgebra, I recall, it means that just this V splits this R of F. So similarly, this T splits R of G. So most of the coalgebra are such morphisms, so morphism from A to C, from B to D, this commutes. And in the middle, due to factorization, you take the image of this factorization factor E on this pair. This is factorization factor E, which was here at the beginning. So this is this image of this pair. So you have such situation. And now, to be a morphism of coalgebras, it means that if you take this splitting of R, F, you take this morphism in the middle induced by E. So it's the same thing as you take this Y below and take the splitting of RG. So this is a very natural characterization of morphisms of coalgebras. So, and in this way, we get a category of coalgebras. And this, as always, is equipped with forgetful functor from coalgebras to this underlying category, which is the category of morphisms. And now it's easy to see that's explained here that the image of this forgetful functor is just the class L of morphisms. In fact, having a coalgebra, then this V makes F a retract of LF. Yes, just this coalgebra structures makes this F a retract of LF, and just it belongs to L because L is closed on the retracts. On the other hand, if you have a morphism L, then just but this morphism F is in L, so then just by lifting property, you split this because this LF belongs to L as well. So just an easy thinking about lifting properties just tells you that this class L is the image of a functor from coalgebras to the category of morphisms. So here this theorem summarizes that. So having an accessible weak factor system in a local category, then L is a full image. So here now, I will tell you what's a full image. So there's a full image of a colimit preserving accessible functor from coalgebras to the category of morphisms. So I see here that I'm switching between, sorry for this, between expressing category of morphism by K square or K arrow. So that should be K arrow, but just this square here was just a, or here that's just a misprint. So, but this is always the same thing. So this, but maybe one has to, so if this factorial system is accessible, so this functor is accessible, then also this functor L is accessible. And having an accessible functor on a category, locally presentable, then the category of coalgebras is also locally presentable. So this is well-known thing. And this forgetful functor from coalgebras to the base category preserves colimits and is accessible. So somewhat you can somewhat concentrate what we know about the situation that L having accessibility to the system. So L is always a full image of a nice functor, colimit preserving, accessible, and the domain is locally presentable. Now, as an example, so take abelian groups and take weak factorial system, which is cofinitely generated by just a morphism from 0 to Z. Then it's immediately clear that cofinite objects coincide with free abelian groups because just you get them by transfinite compositions coming out of these morphisms. And assuming epsilon constructibility, cofinite objects don't form accessible category. this factoring system that has L cannot be accessible. Now this L is taken as a full subcategory of the category of morphisms. So, in fact, my question is, having an accessible vector system, is L always accessible as a full subcategory of morphisms? And this example shows that you cannot expect the positive answer, because even if the system is covalently generated, then having some set theory, so assuming that V is equal to L, then this is not accessible. Why it's not accessible? Because being accessible, then also the full subcategory of covalent objects would be accessible, and it is well known that free abelian groups are not accessible under this axiom because they are not closed under lambda directed collimits for any lambda. So this is example needing set theory that L is not always accessible as a full subcategory of morphisms. But I think it takes, I don't know any example of an accessible weak factorial system in a local category such that L is not accessible. I mean in ZFC. So I don't know any non-set theoretical example of an accessible recurrent system such that this L is not an accessible category. Now this was about L. Now what about R? So this is just a dualization. So if you have accessible recurrent system and local category, so then R is a full image, but now of a limit preserving accessible functor from the category of algebras for this endofunctor R, and again these algebras are locally presentable. So you have the dual result for the class R, and maybe one should start with that because whenever you have covalently generated thing, then R is always accessible in the category of morphisms. That's an easy consequence because it's just by lifting properties, it's given by a set, and then the consequence is accessible subcategory of the category of morphisms. And also nicely accessible because it's embedding to morphisms preserves lambda collimits for some lambda, so this means accessible embedding. Okay. So just what I wanted to say that if we are covalently generated, then R is always accessible, but we don't know whether L is accessible in ZFC, and even we don't, and then of course we don't know it for accessible things. So now another example from abelian groups. So we now take L as split monos and R as split epis. It's easy to see that it's a factorization system, the factorization system, split mono, split epis. Because any morphism factorizes a split mono and split epis in even in a functor, but even in an accessible way. So this is an example of accessible system, which is not covalently generated. Why it's not covalently generated? Because being covalently generated, then this right class, this split epimorphisms, would be closed under lambda collimits for some lambda, which is not possible. Why it's not possible? Because the closure of split epimorphisms under lambda collimits are so-called lambda pure epimorphisms, and in abelian groups, it never happens that lambda pure epis are split epis. So this is an example of a quite natural, accessible system, which is not covalently generated. So it shows that that's interesting to go beyond covalently generated and look at accessible factoring systems. And even more, this class R cannot be accessibly embedded to K squared, which I told you. So then it can't be accessible as with Omega principle, because being accessible, it would be closed and colonies for some lambda. So this is the situation about this right class. So now, again, I told you that it's not easy to recognize whether whenever I give you a weak in a system LR, so it's not easy to recognize whether it's quality generated. And in the same way, it's not easy to recognize, well, of course, if you show that it is, so it is, but if you show that it's not. In the same way, it's not easy to recognize that such a thing is not accessible, because having just those two classes, these factorization functors are not directly determined, so you can have many of them and many factorizations, and you have to show that none of them is accessible. So again, it's not clear, yes? So, but if it is accessible, so then the L injectives, you remember that I showed these L injectives to prove that it's not covalently generated, just that this is not accessible. So, but if it's accessible, so I know these L injectives form a full subcategory of K. Well, that's the definition of them here. So then it's a full image of a limit preserving accessible functor from some locally preservable category to K. So why? We know that this thing is true for R, but to be L injective is the same thing that its unique morphism to terminal object is in R. So just from the fact that this R is full image, we get this injectives are full image. Well, here this explanation, because just you restrict this functor R on the slice category, you get the functor, say, overline R, and this gives you this category of algebras of this functor gives you this N. So just it's immediately clear that whenever R is this full image, so also inject this for this full image. So why I am trying to get this? Because this is a kind of, now I want to show that some weak system is not accessible. So I have some observable property of that L injectives form nice full image. And I will show you that it can be really used to give an example of something which is not accessible. It's important that this is limit preserving an accessible full image, yes? And this is this next theorem. So whenever, totally generally, whenever you have a limit preserving accessible, say kappa accessible functor with M locally kappa presentable, so then the full image is closed in K and the reduced products modulo kappa complete filters. And that's something you can now observe, but just to explain this. So the reduced product, probably everybody knows what's the outer product. So reduced product is simpler. So, and it can be in our situation defined as a category colimits of products along members of this filter. And now, having this, I can give you an example of a weak factorial system which is not accessible. I take the same as the starting example. It means both sets with embeddings. And I will show you that complete lattices, which means injectives, are not closed under reduced product modulo kappa complete filters or any kappa. So let's take a set of candidate kappa and let the filter on this set consisting of subsets whose complement is cardinality smaller than kappa. Yes, which is clearly a filter, and this filter is kappa complete because union of less than kappa of subsets of cardinality less than kappa has cardinality less than kappa. So now you have this filter on a set of kappa, and you take the reduced product of just two element chains. And it is, well, one has to think a little bit, which I think is not proper time to do this, but this thing, I mean, this reduced product of two modulo those filter is in fact the set of all subsets factorized by subsets of quantity smaller than kappa. And I take it, this factorization in terms of Boolean algebra. So this Boolean algebra of all subsets, and I take the ideal of subsets of quantity smaller than kappa. So this is this Boolean algebra, this reduced product. And now take a family of kappa pairwise disjoint subsets of this set I. Each of them is quantity kappa. So we decompose I into kappa subset of quantity kappa. And we take an upper bound of these. So now I want to show now that this is not a complete lattice what we have here, yes? It's not a complete Boolean algebra. So I decompose the I into kappa subsets of quantity kappa, and I choose one element in each one, and I delete this thing from this upper bound. So I diminish this upper bound by deleting just one element in each member of this, which I take upper bound. And this is now an upper bound in my Boolean algebra which is smaller than x. So for any upper bound, you have a smaller upper bound, which means that you cannot have a supremum of these subsets. Yes, the point is that here you deleted a large set of quantity kappa, but on each thing you take just one element out. So this is, yes, I have to say that then I wanted to show that, say, complete lattices or complete algebras are not closed under reduced products modulo kappa filters or any kappa. So I asked this question, map overflow, and this answer was given by Martin Goldstein from Vienna. So this is something which people who do algebras know. So this, in fact, now I think this is the first example of a weak question system on a local category which is not accessible. I mean, the first example with the proof that it's not accessible, and you needed this technology of full images to show it. So now let's go further, and I just want to recall something which is at the beginnings of algebraic weak partition systems. It means that so cofactor generation is just has some smallest condition on the level of sets, one can say. But one can also have smallest conditions on level of categories, which means that you take usually this x square means the right liftings, yes? But now you take it as a category whose objects are liftings together with a chosen lifting function. So here I use notation that a morphism, the object x has underlying morphism. This is this absolute value of x, and I take lifting, but I choose some evidence of this lifting, and in this way, and now I get the category of liftings, and I insist that these liftings are coherent in a natural way. Here is explained that if you have, say, another morphism, if you have another morphism, so then just these liftings are say coherent, it means that the lifting of the if you have the one, the lifting of composition is the morphism followed by lifting for that one, yes. So in this way you get a category of liftings, and this forgetful functor for this category of liftings, the morphism forgets these lifting functions. So this is a kind of scholarization, because to have the right property, some diagonal should exist. And now you take this diagonal and you put a structure on those, so you get a category of liftings, and you get this. And dually you do it with left liftings. So you have this plus square you have on the left side. So this is just this is what Richard Garner did, defining this category of liftings. And just from this follows that if you have this liftings and forget lifting function, so you have a lifting. So always the image of this forgetful functor for this plus square belongs to this ordinary square. And now we say that the weak factorial system is small generated if there is a small concrete subcategory whose plus square is R. Yeah, so again, maybe just to show it this way. So what does it mean to be covalently generated? It means that this, just for liftings, you can adjust a set of things. Now you assume that you have just a small category of things. Yes, such that this new lifting, this category lifting, is generated by a small thing. So it is small generated. And again, that's a consequence of small jet argument that any cofiber generated is small generated. And what's now interesting is that accessible exactly corresponds to small generated. Yes, so this accessibility condition, it means existence of accessible factorization is equivalent to being small generated. So now you can order weak factorization systems following left classes, and it's clear that you have both for combinatorial and for accessible. We have small joints in the resulting ordered set, ordered class, such that it's generated by unions. Unions of generating sets, yes, because you have just anything generated by set, you take the union, and so it generates the union. And also it's true for intersections, for meets, but this is much more delicate because for combinatorial, it follows from my joint paper with Michael Mackay, which is based on something we call fact argument. So it follows that you have small needs. In fact, if you have a set of covalently generated and you take intersections, so it's again covalently generated. And Simon Honoré somewhat transferred this also to accessible. So also accessible have small needs. So this both accessible and covalently generated weak factorial systems have small needs and small joints. Of course, one can say that the model category is accessible if case locally presentable, and it's both weekend systems are accessible. So this coincides with definition given by Emily Riel in 2011, because that's one additional condition we just follows from just this definition. So this is in the same way as you define covalently generated, you define accessible model categories. You know that in covalently generated model categories, W is always accessible. Here, well, I don't have examples. I think maybe I have, but you cannot show that it's accessible, but you can show that it's a full image of an accessible functor. It means that's an accessible category, an accessible functor, that is a full image of this. And under some set theory, having proper class of almost uniform cardinals, so V is pre-accessible and pre-accessible embedded. It means, pre-accessible means that from accessible categories you take just the smallness condition and not the existence of filtered colimits or capable colimits. And pre-accessible embedded means that the existing capable colimits are preserved. So, but that's one somewhat frustrating open problem here, whether there is something like Smith's theorem for accessible model categories. The Smith's theorem is a very nice and applicable recognition theorem which can tell you that something is cofibrily generated. One would like to have something similar for accessible model categories, which is not known. I don't know whether it's possible, but it's not known. So you can also order model categories, but now following weak equivalences. And I take model categories the same cofibrations. So you see, before I ordered weak fractional systems by cofibrations. Now I take cofibrations fixed and I order model categories with weak equivalencies. And following Smith's theorem for combinatorial, it follows that combinatorial model structures with the same cofibrations have small meets, where the meet is given by intersections of weak equivalences. You see, the Smith theorem basically says that to be regenerated, you need that these weak equivalences are accessible. An intersection of accessible is accessible, so one has small needs. But under Wopjenka's principle that we showed with Walter Tollen in 2002, that assuming Wopjenka's principle, they have all meets and all joints. So in particular, there's the smallest one. So you have a locally controlled category, and you have covalently generated cofibrations. And you would like to know whether the smallest W making a model category out of this. Jeff Smith claimed that this is true, but we could show that it's not a Wopjenka's principle. So that's now a question whether it's true without that theory or not. No counterexample is known. So whether you really need for this minimum model structure, we call it let determine with Tollen, whether you need a set theory, whether you need to cheat or whether just it is true. So in that paper I mentioned, that was a quite evident procedure how you generate. So you start with L, which is called covalently generated. So you have this corresponding R. And now you take the smallest class of weak equivalences such that any trivial cofibration, any trivial fibration is weak equivalence. Then weak equivalences should satisfy 2 out of 3 properties. So you take this. And this intersection of the equivalences is cofibrations. It is trivial cofibration, should be equal to the push-out transient composition retracts. So these are, say, closure condition, which you immediately get of this class W, which can serve as weak equivalences for L. And then you take the smallest one. The smallest one, it means this generated from R by this closure condition. And now you ask, is this a combinatorial model category? So if it is, of course, it's the smallest one. But the question is whether it is, yes? So under Wopjenka's principle, it is. Yes. So that's one thing which one can show. This is something which is expectable, but one has to prove it, and it follows again from Smith's theorem that it is combinatorial if and only if this transfinite procedure stops. So we start with, say, I start with R, this is W0, and then now the second step I close it under 2 out of 3 property. Then I intersect it with L, and I close it under retracts, under push out transcontinental retracts. And now I repeat, I close the resulting thing under 2 out of 3. I close the intersection and so on and so on. So here I get in effect just a transfinite series of classes, and the resulting W, which is union of those, is combinatorial if and only if it stops. So one direction is evident, because if it stops, so then this thing you have is accessible and that it's true. But from the use of Smith's theorem, you can show that if it stops, so if it's combinatorial, it stops. But of course, the question is whether it ever stops or not, yes? And recently, that's the kind of breakthrough result of Simon Honore. He proved that, without any set theory, he proved that it stops, he proved that the smallest one, assuming that L is tractable. So this is slightly more special than cofinitely generated. It means it's generated by a morphism with cofinite domains. So if it's tractable, so then he proved that you have the smallest thing. So this is highly non-trivial thing, because it generalizes, say, that was Denis Charles-Szysinski who practically at the same time as he did show that on toposes you have the smallest thing. Then my student Mark Olshok just generalized this Szysinski to something more general, but that's a beautiful result of Simon. That when it's tractable, then always stops, so that you achieve this combinatorial one. And for that he used his concept of a weak model structure somewhat. He showed that the smallest one is weak, and it's a real one. So that's highly non-trivial and a very soon result. You can ask the same question also with accessible. Nobody look at this. So again, you would start this accessible L, which means that it is more generated, and you would like to know whether the smallest one or not. So I don't know anything about that, but that's the question. So that's, I think, all what I wanted to tell you. That are just references which I used. So that was this old paper, which is the first example. Then this is this Simon Henry's archive preprint from last year, and another one also, which is this paper is Mackay about several categories. Emily Real defined accessible model structures here, and these are 2 papers of mine, and this is the most recent one in some sense, which I followed in my talk, and this is the old paper with Rapatola. So that's all what I wanted to tell you. So thank you for your attention.
Jirka, thank you very much. As you well remember, we shared your birthday not long ago in Barcelona, and now you are sharing mine. So thank you very much for the talk.
But Carles, but the main pleasures of sharing disappeared.
Yes. Well, you know, there have been, I think, 4 books which have been absolutely crucial in my mathematical career. So I think the first was Hilton Mislin Royberg which was published in 1975. Busfield Kahn, which was published even earlier, 1970. A little later, Farjun's book on cellular structures, 1996, and Adamek Rosický. I mean, Adamek Rosický was kind of a discovery, because I had been in mathematics for quite a number of years. And which just unraveled a completely new area of mathematics, which I did not know but was crucial to our research in homotopy theory. And suddenly, I must say, with a shame that we discovered the Prague school and we discovered a new world full of marvels. And well, since then, of course, I was lucky enough to collaborate with you. I have learned a lot with you, and I think that probably the deepest papers in my career have been written jointly with you. So thank you very much. You know the anecdote, because I told you that there was a Friday evening in 1995 when Jeff Smith, after we had been talking a little bit, he went to my office and then he borrowed Adamek Rosický's book from my shelf. And the Monday after, combinatorial model categories had been invented, and most likely Smith's theorem had already been proved. So, I mean, your influence in homotopy theory has been enormous, and we all thank you for this. I only have one question. As you explained earlier in your talk, the fact that the factorization system is accessible depends on set theory. And you have explicit examples. But as I understand, the fact that the category is accessible does not depend on set theory, right?
No.
And the question is, does the fact that the model category be accessible depend on set theory?
No, sorry, how? So what's the question? If I can you repeat it, Carles, please?
Yes, if the fact that the category is accessible depends on set theory, and the fact that the model category is accessible in the way you have defined it depends on set theory.
In which sense?
Do you have an example of a category which is accessible or not accessible, depending, for example, on Vopenka's principle?
Yes. Yes. For instance, free-abelian groups. Yes, just the accessibility depends on set theory. Yes.
Even abelian groups.
Mm-hmm.
Okay, thank you.
That was your question. So just you have a category and you would like to, that is accessible, but it depends on set theory, yes? Yes. So there are natural, like these three groups, yes? I mean, that's are natural examples that it can happen, yes.
Thank you.
So thank you, Jiří, for your talk. Are there any more questions?
May I ask?
Sure.
Yes, I just wanted to make sure what there was one question which seemed to be open, if I understood it correctly. So you told that if you have a cofibrantly generated weak factorization system in a locally presentable category, then there is no example where it would be in ZFC provable that the left-hand side part is accessible or accessibly embedded. Oh, sorry, is not accessible. Okay, it's interesting. This is still...
No, but Jan, you see, because of course, immediately it came to your mind that you can take contortion theories and to look at these examples, yes. And even I asked Jan Terlify, maybe you also about this, and it seems that you don't have any example of such situation, yes, in your package of examples.
I think I remember you asked about that, but it still sounds strange to me that this is not resolved. because it's strange. There doesn't seem to be any obvious reason why it should be, but accessible. But okay, if there is no proof that it is not. Okay, thank you.
Okay, so if there are no more questions, we thank Jiří again for his talk. Thank you.